Have you ever wondered how calculators compute values like e to the power of 1.5 so quickly? They don't use infinite tables, instead, they use Taylor series. This mathematical tool allows us to represent complex, transcendental functions as simple sums of polynomials, making impossible calculations manageable and precise. In physics and engineering, we often encounter functions that are too difficult to solve analytically. By approximating these functions with a Taylor series, we can turn a difficult differential equation into a simple algebraic one. This is the foundation of modern computational science and numerical analysis. Before we build the series, remember the unique property of e to the x: its derivative is always itself. Whether you differentiate it once, twice, or 100 times, the rate of change remains e to the x. This consistency is exactly what makes it the perfect candidate for our first Taylor expansion. A power series is essentially an infinite polynomial. Our goal with the Taylor series is to find the specific coefficients, those an values, that make our polynomial match the behavior of our target function perfectly at a specific point of interest. This is the general Taylor series formula. It tells us that to approximate a function near a pointer, we sum up the derivatives at that point, divided by the factorial of the degree, and multiplied by the distance from a raised to that power. When we choose the center point to be 0, the Taylor series is specifically called a Maclaurin series. For the exponential function, centering at 0 is the most common and simplest way to demonstrate how the approximation builds up term by term. Let's start our approximation of e to the x. At x equals 0, e to the 0 is 1. Our zeroth order approximation is just a constant horizontal line at y equals 1. It's accurate at exactly 1 point, but we can do much better than this. To improve the fit, we match the first derivative. Since the derivative of e to the x is also 1 at the origin, we add the term x. Now we have a linear approximation, y equals 1 plus x. Notice how the line now follows the curve's direction for a short distance. Next, we match the second derivative to capture the curvature, or concavity. We add x squared divided by 2 factorial. This creates a parabola that hugs the exponential curve even more closely, extending our range of accuracy further away from the center point. A pattern is now visible. Each subsequent term adds a higher power of x divided by its corresponding factorial. These factorials grow very quickly, which ensures that higher-order terms become smaller and smaller, allowing the series to converge toward the true value of the function. Let's use the first 5 terms to estimate the value of e itself by setting x to 1. Summing these terms gives us 2.708. Compared to the actual value of approximately 2.718, we are already within 1% accuracy using just 5 simple terms. If we try to estimate a value closer to our center, like e to the 0.1, the series converges even faster. With only 3 terms, we achieve incredible precision. This demonstrates that Taylor series are most effective when the input is near the point where the series was centered. The difference between the actual function and our polynomial is called the remainder or the error. Visually, you can see the red and blue lines eventually diverge. To minimize this error for values far from 0, we would either need more terms or a different center point. Watch as we increase the number of terms. As e approaches infinity, the polynomial wraps itself around the exponential curve across the entire number line. For e to the x, the radius of convergence is infinite, meaning it can represent the function perfectly everywhere if we use enough terms. Unlike some functions like the natural log, which only work within a specific range, the Taylor series for e to the x is valid for any value of x. Whether you are calculating e to the power of 5 or negative 50, the series will eventually converge to the correct answer. One of the most beautiful applications is proving Euler's identity. By plugging I times x into our exponential Taylor series and separating the real and imaginary parts, we perfectly recreate the Taylor series for cosine and sine. This reveals a deep, hidden link between trigonometry and exponentials. In engineering, we often use small signal models. If x is very small, we can ignore the x squared and higher terms entirely. This leaves us with the linear approximations 1 plus x, which is much easier to use in real-time calculations for sensors or control systems. Taylor series are mathematically robust. If you differentiate the series for e to the x term by term, you get the exact same series back. This confirms our calculus remains consistent even when we treat functions as infinite sums of polynomials. What about e to the negative x? We simply substitute negative x into our formula. This creates an alternating series where the signs flip between positive and negative. This series converges just as reliably, oscillating toward the true value with each added term. A common mistake is forgetting the factorial in the denominator. Without the division by n factorial, the terms grow way too large, and the series will fail to converge. Always remember that the factorial is what attains to the power of x and makes the approximation work. Another pitfall is using a series centered at 0 to estimate a value very far away, like e to the 10th, with too few terms. While it will eventually converge, it is inefficient. For values far from 0, it is better to recenter the Taylor series closer to your target value. Don't underestimate the truncation error. If you need 10 decimal places of accuracy for a scientific calculation, a second-order polynomial won't be enough. Always check that Lagrange error bound to determine how many terms are necessary for your required level of precision. To summarize, the Taylor series turns the exponential function into an infinite sum of powers. We build it by matching derivatives at a center point. For e to the x, the derivatives are always 1 at the origin, leading to a simple, elegant pattern involving factorials. Let's test your knowledge. What is the third-order term of the Maclaurin series for e to the x? If you said x cubed over 6, you're correct. Remember, the denominator is 3 factorial, which equals 3 times 2 times 1, giving us 6. Mastering Taylor series opens the door to understanding how complex systems are modeled in the real world. From calculating interest rates to predicting planetary orbits, these approximations are everywhere. Thank you for watching. Generated by Vision Solve AI.